Hello everyone, I'm Damien, and I work as a scientist for Tumult Labs, a startup working on differential privacy. Today, I'll tell you a story about data protection and open data. Once upon a time, the Department of Education wanted to answer a simple question. How much do new graduates earn after completing their degree? And how much does that number vary according to institution, fields, type of degree, demographics, etc.? Having data to answer this question could be useful for three groups of people. The first one is economists and social scientists. They can use this data to study trends and changes in labor markets, for example. Public agencies can also use this data to quantify and adjust the impact of their education policies, for example, regarding funding. And last but not least, students can make better choices regarding the choice of their degree, the terms of their student loans, and maybe in even negotiating their first job offer. So the question is, how do we collect this data? Here's one option. We could ask new graduates what their first salary is, collect their answers, and publish these answers, after, of course, removing the name of each student and other identifying information. Here we censored the first column of the dataset, presumably containing all of these identifiers. There are two big problems with this approach, unfortunately. The first one is that many people don't answer surveys. Here, only 2 out of 5 people answered. In practice, the number could be even less. Low response rates tend to make the data unreliable. The fewer data points you have, the more error ends up in your statistics. Even worse, low response rates can introduce sampling bias. Maybe the people who answer the surveys have larger or smaller salaries than the people who don't. The impact of these low response rates can even be hard to quantify and take into account when using the data to do science. But that's not great. The second problem is that removing identifiers isn't really safe. The anonymization community in academia has known it for years. De-identification is just not a robust way of preventing people from re-identifying users and getting sensitive information. There are successful attacks that people have run on de-identified data where attackers can find clever ways of figuring out identifying information even if everything seems to have been censored. So these are the two big issues, but there's even more bad news. These two problems tend to make each other worse. If people know that their data is going to be published without adequate privacy protection, then they're even less likely to answer the survey. The lack of privacy protections can hurt response rates, which in turn hurts accuracy. And the fewer people you have in your data, the easier it is to re-identify them. So protecting them adequately becomes harder and might come at an even steeper cost in utility. So the fewer people you have, the less private your statistics become, and the fewer people end up in your data. So what can we do? Well, we could try some other ways to obtain the data. For example, we could ask the Internal Revenue Service, the tax office in the US. They know everybody's salary because they have everybody's tax returns, so they could simply compute this data for us and share it with us if we ask nicely. The problem, of course, is that the IRS can't simply give us that data. Indeed, they are bound by law to protect all of the data they have and not reveal how much income a specific person declared. In fact, they can't even reveal whether anyone in particular even filed their taxes. Most organizations have similar constraints. They can't just publish the sensitive data they hold, even when they want to. So how do we enable them to do that? Releasing statistics without revealing individual data. Let's try to think about how to capture this property. Say that the IRS publishes some data based on the information they have. The goal is to make sure that this data does not reveal anything specific to a single individual. One way to achieve this would be to say, what if we remove someone from the original data? We shouldn't be able to detect it. Otherwise, if we can detect the difference, maybe that difference leaks some information specific to the removed row. That's an interesting idea here. We must not be able to notice if someone was removed from the input purely based on looking at the output. How do we capture that information? First, I will note that the goal is still to release useful data. We must be able to say useful things about global trends in the data. Here, imagine you have data points that look like this, and their average ends up here. Then if the data points are over here instead, then we really want to return a very different value for the average. And that's working as intended. We want to be able to do that. We want to be able to release accurate statistics which tell us something meaningful and interesting about the data, globally, or about large groups of people. But now, suppose that our second database is almost the same as the previous one. There's only one data point of difference between the two, just like we said before. Then if all we do is compute the average, we can see a change here. It's a small change, but it's still observable. So someone who cross-correlates multiple statistics or has some auxiliary information about the data could get some information about this individual data points, or even re-identify people based on the data we publish. In practice, re-identification attacks are often more complicated, but fundamentally this is sort of how they work. They combine information from different sources. Each piece of information on its own might not seem revealing, but the combination is where everything can often break down. So how do we fix it? The key insight is going to be to add some perturbation to the output. Instead of returning the exact number, we add some jitter to it. In practice, we're going to sample some random number. Let's say we roll a die and we look at what the die is telling us, and then we add it to the results before returning it. We call this jitter noise. We add noise to the data. That makes our algorithm randomized. If we run it multiple times, we might get a different answer. But that means also that for each answer you can get from one database, you could have gotten it from the other with similar probability. Note that it doesn't hinder our utility goal too much. The noisy answer is still close to the real answer. Datasets that would return very different answers without noise will still be very distinguishable after adding noise. We're going to get some slightly less precise statistics, but they can still be good enough to make strong scientific statements about global trends in the data. This idea of adding noise and making closed databases indistinguishable when you look at the output, that's the core intuition behind a concept we call differential privacy. Differential privacy, which we abbreviate DP, is simply the mathematical formulation of what I just explained. It has many benefits. First, it gets rid of security by obscurity, which was often necessary using past techniques. The privacy guarantee it gives us works even if we explain exactly what privacy technique was applied to the public, even if we publish all of the details of our anonymization strategy. And that's great for people working with the data afterwards, because they can take into account everything that was done to the data in their statistical analysis. Second, it gives us a provable, quantifiable guarantee. We can make formal statements about what probabilistic information an attacker can gain. This is captured by a parameter we call the privacy loss, typically denoted by the Greek letter epsilon. The lower the epsilon, the better the protection. Third, differential privacy composes. If we release multiple statistics on our data, we can add the privacy loss from both and get a guarantee for the overall publication. That's really convenient, because it means we can do very complicated operations on the data that are just combinations of simpler parts, and it's easy to keep track of the overall privacy loss. Okay, let's dig a bit deeper into this quantifiable guarantee thing. What does this look like in practice? Let's go back to our intuition from earlier. We said that if we compute the same thing from two databases, where one has had one record removed, we shouldn't be able to detect the difference. In practice, we're going to capture this idea with saying that any results can be obtained with similar probability in both cases. For example, we can say at most, it's at most twice as likely to obtain a certain output from the second database than from the first, or from the first to the second. Let's say we use this twice as likely bound. How do we now decide what kind of noise to add to the data in practice? Suppose we're counting people with brown hair in a specific neighborhood. We want to publish this statistic safely, privately. We're going to imagine here that the real value is 100, and we're going to calculate, compute, visualize the probability of returning a certain output using this real value 100. Of course, we want to be able to return this exact value with some probability, right? Ideally, as much probability as we can for the utility goal. That means that if the real value is 101, we're going to return 101 with the exact same probability, right? It means that it's the probability of adding zero noise to the data. Now, how likely are we to return 100 if the real value is 101? We said that this probability must be the same as if the real value was 100. We want these two situations to be indistinguishable up to a factor of 2 in the likelihood. We want this to be as small as possible because we're not returning the right answer, but we're bounded by this twice as likely bound. So to make it as small as possible, it means making it exactly half. That gives us the probability of the noise being -1, which also gives us the probability of returning 99 if the real value is 100. Now we can continue this reasoning. How likely are we to return 99 if the real value is 101? Again, we want it to be as little as possible, so exactly half that, because we can't go below this. We can continue this reasoning to decide the probability distribution on the left side, and the same happens on the right side of the curve. If you look at the bars from a single color, you see a pointy probability distribution shaping up. And if you follow all that, congratulations. You're now familiar with the fundamental building block of differential privacy, the Laplace distribution, here in its discrete version. That's how you make simple statistics like counts differentially private. Of course, it gets much more complicated for more complex use case, but hopefully this sort of reasoning provides you with an intuition about what we have to do to make statistics differentially private. So I said differential privacy had lots of advantages. It also has some costs. The first one is a mindset change. People can no longer ignore the noise, ignore that noise was added to the data, especially if we make the algorithm transparent. They have to take this new source of uncertainty into account in their statistical analysis. In a perfect world, this wouldn't be a drastic change. Uncertainty was there all along. All of the data has some uncertainty, noise, data quality issues in it. But in practice, this idea of adding noise, artificial noise to the data can often create some resistance. So to overcome this, you really have to double down on transparency. For example, by providing error measures like confidence intervals on the output data. The second change is related. Differential privacy gives us this great parameter epsilon, which gives us a formal guarantee. But how to choose the right value? The fact that DP is so transparent and explicit means that you can no longer sweep this under the rug and hand wave some vague notion of it looks safe enough to release. You have to make these difficult decisions. Finally, implementing differential privacy in practice is very difficult. There has been a lot of theory research on differential privacy, but comparatively little investment in tooling. And it turns out that there are many challenges with actually writing correct, useful code to implement it. At Tumult Labs, we're investing a lot into this. And we're writing software that makes it easier for people to use differential privacy, even if they're not experts. I'll talk a bit more about the platform aspect at the end of this talk, but first I'll focus on the second aspect. What does that choice of epsilon, of privacy loss, look like in practice? The first thing to do is to give an explanation of what epsilon means, using understandable terms. Let's go back to the goal of differential privacy. Preventing someone from learning anything about any individual in the data. So let's represent someone who wants to break this goal. They want to get information about a specific individual. We want to prevent them from getting information about someone, for example, whether they are in the data or not. Instead, we want them to stay uncertain about the target they're trying to re-identify. Now, how do we quantify this goal? My favorite intuition is betting odds. Suppose that at the beginning, the attacker is uncertain about whether the person they want to target is in the data or not. If they had to bet, they would give 1-to-1 betting odds that the answer is yes or no. They would be okay making a hypothesis about the target, betting €1, and if they're correct, winning €1 back. An attacker that gains a lot of information about an individual means that by looking at the output data, their betting odds change by a lot. For example, they could go from equal odds to a posterior suspicion of more than 99% that their target is in the data. They go from being 50% sure to being 99% sure. In that case, they're so certain about it that they would be willing to bet €100 just to win a single euro. Conversely, if their odds can't move too much, regardless of what data was generated, then we're fine. It means that they haven't changed their level of certainty by a lot. In other words, they just haven't learned much about their target. There's a direct relationship between epsilon and this notion of how certain can an attacker get. Note that the line here never gets exactly to 100%. Each individual in the data has some plausible deniability, always, just not very much if epsilon is very large. This is one of the reasons why differential privacy is very strong. It means that anything that would reveal exactly some information about an individual with absolute certainty is simply forbidden. It just cannot happen. No matter how smart or complex your attack is, you simply cannot do better than this line. This is why we say that this differential privacy is future-proof. No matter what new attacks are invented in the future, they will never go beyond that line. Okay, what does it look like in practice when institutions are trying to publish data with differential privacy? Here, typically, like here we're taking the IRS as an example, but such institutions start by setting a goal privacy budget, considering factors like intuitive explanations like the one I've just given, precedent from previous data releases, sensitivity of the data, etc. Then, with some help from us, they try out a first strategy to generate data. They evaluate this first prototype and communicate about the error to the people who will consume this data. This initial strategy, it rarely works on the first try. We typically have to, they typically get some pushback, and people ask if you can, for example, increase epsilon to get more precise results, maybe at some cost in privacy. But you often have more tools at your disposal than simply increasing the privacy budget. For example, you can allocate more of your total epsilon to some queries and less to others. Often, during this iterative process, you learn more about what your data customers actually want and adapt accordingly. There are many tools at your disposal to optimize a differentially private publication. I already mentioned splitting the privacy budget in a different way, like so. Another thing you can do is computing fewer aggregations. It's a more extreme version of the previous technique. You free up some of your total privacy loss budget by dropping some statistics completely because they're less important to you. Another thing that is often very, very useful is aggregating the data more coarsely. For example, instead of slicing and dicing the data by age, you use age ranges. These are just a few examples. There are a lot more things you can do to optimize the privacy accuracy trade-off. The iterative process I mentioned earlier often takes some time. Part of what we do is facilitating these discussions. We explain options, come up with creative optimizations, and build dashboards to let people experiment with different strategies. After some time, we end up on a strategy that often is fairly different than what we started with, and it makes the data users happy. At the end of the process, you're able to confidently publish data while sleeping well at night, because you know that you've protected it in a robust, principled way. Here, the data shared by the IRS to the Department of Education ended up on a public website called the College Scorecard. But wait, we missed a step before getting to that point. Let's go back to the process that enabled us to go there. First, we collected requirements, right? What problem are we trying to solve? Then we built the prototype algorithms, measured the error, and iteratively improved the strategy until error levels are satisfactory. That leaves the last stage, deployment. How do we actually roll this out to production? As I mentioned before, transforming all this theory into code that works in practice is harder than it seems. Real-world workflows often have multiple datasets and want to do complex transformations on the data. So we need to follow the flow of data, reason about the maximum impact that any one user can have, and add noise accordingly. Behind the scenes, this requires a fair bit of complicated logic. Second, differential privacy is a little bit like cryptography. Small, innocuous-looking implementation bugs can have a big impact on privacy guarantees. At Tumult, we do a bit of adversarial research, and we found a few vulnerabilities in open source software to make sure that our software is resistant against these kind of things. Finally, scalability is a hard constraint for pretty much all our customers. But making algorithms that can run on very large datasets isn't always a priority in research papers, so we often have to adapt or invent new techniques. To add some more complications to the mix, all these requirements can conflict with another design goal, which is user-friendliness. We want all data scientists and engineers to be able to use differential privacy, not just people with PhDs in the field. So how are we tackling that challenge? We designed and we built a platform in two parts. First, Tumult Core is the rock-solid foundation on which everything else is built. It implements a very extensible framework based on academic collaborations with institutions like Harvard and Microsoft. This framework is composed of building blocks, which correspond to individual transformations or measurements on the private data. A programmer using Tumult Core can take these building blocks, assemble them to implement very complex algorithms, and the framework will provide a privacy proof that the overall mechanism is differentially private, for free. This property is fundamental to making our software robust. All we have to do is test and audit small components that are easy to review and audit, and the overall safety property follows. Importantly, of course, all these building blocks use Apache Spark to do the actual computations on the data. This ensures scalability, which is a crucial design goal for the platform. Tumult Core is for power users, experts in differential privacy who write their own mechanism by hand. That's why we built a layer on top of it, which we called Tumult Analytics. It's an easy-to-use API made for non-experts. Its interface in Python will feel familiar to anyone with prior experience with Spark or Pandas, and hides away as much complexity as we can. The user tells us what they want to do, and we automatically assemble the right building blocks to return an optimized result. Tumult Analytics has a simpler interface, but it's still very powerful. All of our customer deployments use Tumult Analytics. So it's currently running on production systems at institutions like Wikimedia, the IRS, and the US Census Bureau. Oh, and the good news is the platform is now open source. We are doing this month, in July 2022. Open source is central to our strategy at Tumult. We think that transparency and auditability are essential to building trust, and trust is key to adoption. That's all I had for this video today. Feel free to send me any questions or comments at the contact info over there. We're also hiring software engineers and scientists, so you can look at our careers page for more information. And if you'd like to meet us or talk to us about your problem about releasing data, you can go to tmlt.io/connect to book a meeting with one of us, and we can help you understand how well can the techniques we're developing help you publish or share data safely.